Welcome to this rigorous scientific lecture on using artificial intelligence to accelerate patent success. Today, we'll explore systematic workflows for improving invention disclosure quality and optimizing prior art search habits. Let's begin with a fundamental question. Why do most patent applications fail or get significantly narrowed during prosecution? The answer lies in two critical areas: inadequate invention disclosure and insufficient prior art analysis. According to USPTO data, approximately 40% of rejections stem from inadequate disclosure under Section 112, while 35% arise from prior art issues under Sections 102 and 103. These aren't independent probabilities, leading to roughly 60% of applications facing significant challenges. Let's do a quick back-of-the-envelope calculation. What does this failure rate cost? The average cost to prosecute a patent through final allowance is approximately $15,000, including attorney fees and USPTO charges. With a 60% failure or significant narrowing rate, the expected wasted cost per application is $9,000. This represents resources spent on claims that ultimately get rejected or severely limited. For an organization filing 100 patents annually, this amounts to $900,000 in inefficient spending. This is the baseline we're trying to improve. Now let's discuss how artificial intelligence can systematically address these challenges through a structured workflow. The key is not to replace human expertise, but to augment it with computational power. Phase 1 focuses on enhancing the quality of your invention disclosure using AI as a critical review partner. Step 1A. The inventor creates an initial disclosure document describing the problem, solution, key features, and differentiating aspects. This is the raw material we'll refine. Step 1B. Feed this disclosure to a large language model with a specific prompt, asking it to identify gaps, ambiguities, missing implementation details, and potential claim limitations. Here's a structured prompt template. You ask the AI to analyze for missing technical details, ambiguous terminology, unstated assumptions, implementation gaps, and potential claim limitation risks. The AI returns a structured critique highlighting these issues. Step 1C. Use the AI feedback to iteratively refine the disclosure. Each iteration should add specificity, clarify ambiguities, and expand on implementation details. Aim for 3 to 5 iterations. How do we quantify whether our disclosure has improved? Let's define a simple completeness metric. Completeness C equals the number of detailed technical elements divided by total required elements times 100%. A detailed element includes specific values, ranges, materials, or algorithms rather than generic descriptions. In practice, initial inventor disclosures typically score 40 to 50% on this metric. They describe what the invention does, but lack sufficient how detail. After 3 to 5 iterations with AI feedback, disclosures typically reach 75 to 85% completeness. This represents a 50 to 70% improvement in detail density. Phase 2 addresses the prior art challenge. Here we leverage AI for comprehensive search and overlap analysis. Step 2A. Use AI to extract all technical concepts, features, and claim elements from your refined disclosure. This creates a structured taxonomy of searchable elements. The AI maps your core concept and features into multiple search query sets. Each feature generates several semantically equivalent queries to ensure comprehensive coverage. Step 2B. Execute searches across multiple databases. Use Google Patents, USPTO database, eSpace.net, and domain-specific technical literature databases. I can automate query submission and result aggregation. Step 2C. This is where AI provides tremendous value. Use embedding models to compute semantic similarity between your invention and each prior art reference. This goes beyond keyword matching to understand conceptual overlap. The similarity score S between your invention I and prior art J equals the cosine similarity of their embedding vectors. This produces a score between 0 and 1, where 1 indicates identical technical content. Let's discuss how to interpret these similarity scores with scientific rigor. Scores from 0.9 to 1.0 indicate critical overlap risk. These references likely disclose your core concept and multiple key features. Immediate review required. Scores from 0.75 to 0.9 indicate significant overlap. These references share your core concept but may differ in implementation details or feature combinations. Scores from 0.5 to 0.75 show moderate overlap. These references address similar problems but with different approaches. Useful for establishing technical field and identifying differentiation opportunities. Scores below 0.5 indicate low relevance. These can generally be deprioritized unless they contain specific features of interest. Phase 3 involves systematic documentation of your analysis. This creates a clear record for patent professionals and reduces back-and-forth iterations. Step 3A. Create a feature comparison matrix. List your invention's key features as rows and top prior art references as columns. Use AI to populate this matrix by analyzing each reference against each feature. This matrix immediately reveals where your invention differs. In this example, while individual features may exist in prior art, the specific combination is novel. This is your differentiation story. Step 3B. Document all experimental evidence systematically. For each claimed advantage or unexpected result, maintain a structured log with dates, parameters, results, and controls. Use this template for every experiment. Include date, objective, method, specific parameters, quantitative results, control comparisons, and statistical significance. This documentation is invaluable during prosecution. Step 3C. Use AI to generate concise summaries of each relevant prior art reference, specifically highlighting what it teaches and what it lacks relative to your invention. Phase 4 uses all the accumulated data to perform quantitative risk assessment and inform claim strategy. Let's develop a simple but rigorous risk scoring model for prior art overlap. The risk score R equals similarity S times criticality C times feature count F. Similarity is the embedding score we discussed. Criticality is a weight from 0 to 1 based on the reference's jurisdiction and date. Criticality C equals jurisdiction weight times date weight. For example, U.S. patents get weight 1, foreign patents get 0.7, and publications get 0.5. Date weight is 1.0 if the reference is less than 20 years old, decreasing linearly for older references which may have expired or been superseded. Let's work through a concrete example to make this tangible. Consider U.S. patent 9,876,543 from 2018. Our semantic analysis yields a similarity score of 0.82, indicating high overlap. It's a U.S. patent less than 20 years old, so criticality is 1.0. It matches 4 of our 6 key features based on the comparison matrix. The risk score is 0.8. 2 times 1 times 4 equals 3.28. On our scale, anything above 3 is high risk requiring detailed analysis and potential claim strategy adjustment. Now you might ask, how exactly do we use this risk score in practice? Let me answer that. Risk scores inform your claim hierarchy strategy. Higher risk scores suggest you should draft dependent claims that explicitly recite differences from that prior art. They prioritize which references your patent attorney should review in detail versus which can be briefly noted. They guide continuation application strategy by identifying which features provide the strongest differentiation for future filings. Phase 5 is about packaging all this analysis into a format that maximizes efficiency for your patent professional. Deliverable 1. A one-page executive summary with invention title, problem statement, solution overview, key differentiators from top 3 prior art references, and recommended claim strategy. Deliverable 2. Detailed technical disclosure, 5 to 10 pages, with all implementation details, experimental data, alternative embodiments, and figures or diagrams. Deliverable 3. Prior art analysis, 3 to 5 pages, including the feature comparison matrix, risk scores for top 10 references, and AI-generated summaries of critical references. Deliverable 4. Supporting data package with experimental logs, raw data files, source code if applicable, and CAD drawings or schematics. Let's analyze the time investment and economic return of this AI-accelerated workflow versus traditional approaches. Here's a realistic time comparison. Traditional disclosure preparation takes about 8 hours. With AI assistance, it drops to 4. Prior art search traditionally takes 12 hours, but AI reduces this to 5. Documentation and analysis similarly see 50 to 67% time savings. Overall, you save 57% of inventor time. Now let's translate time savings into economic value. Assume an effective inventor cost of $150 per hour, including salary, benefits, and overhead. We save 17 hours per disclosure using the AI workflow. That's $2,550 saved per patent application just in inventor time. But the bigger value comes from quality improvement. If we reduce the failure rate by 30% through better disclosures and prior art analysis, we avoid $9,000 times 0.3 equals $2,700 in prosecution costs. Total value per patent is $5,250. For 100 patents annually, that's $500,000 in value creation. Let me share an advanced technique, systematically tracking how prior art evolves in your technology space. Set up automated monitoring of new patent publications in your technical classification codes. I can process these weekly and flag any that exceed your similarity threshold. Maintain a living database of relevant prior art with similarity scores that update as new references are published. This provides early warning of crowding in your technology space. Use trend analysis to identify which features are becoming more crowded versus which remain open. This informs R&D investment decisions and continuation application strategy. Here's a trend graph showing increasing prior art density over time in a hypothetical technology area. This upward trend signals that you should prioritize filing sooner and consider broader continuation coverage. You might ask, what about false positives? Doesn't AI sometimes flag references that aren't actually relevant? This is an important concern. Yes, false positives do occur. I might flag a reference as similar based on superficial keyword overlap, without understanding the technical distinction. The solution is two-stage filtering. Use AI for the first stage broad sweep with a lower threshold, then apply human expert review for the second stage to eliminate false positives. In information retrieval terms, precision equals true positives divided by true positives plus false positives. With proper threshold tuning, you can achieve 70 to 80% precision. Recall equals true positives divided by true positives plus false negatives. AI excels at recall, typically achieving 90 to 95%, meaning you rarely miss relevant prior art. For patent applications, high recall with moderate precision is the optimal trade-off. It's better to review a few false positives than to miss a critical reference. How does this AI workflow integrate with your existing patent processes? Let's map out the touch points. Touchpoint 1. At initial invention capture, the AI prompts inventors with structured questions to elicit complete technical details from the start. Touchpoint 2. During pre-filing review, the patent committee receives the comprehensive package we described, dramatically improving decision quality and speed. Touchpoint 3. At attorney handoff, the structured documentation reduces the attorney's ramp-up time and first draft cycles, saving significant legal costs. Touchpoint 4. During office action responses, the prior art database you built enables rapid identification of distinguishing features and experimental evidence to overcome rejections. Let me share a sanitized case study from a mid-sized technology company that implemented this workflow. Before implementing the AI workflow, this company had a 45% first office action allowance rate and averaged 3.2 office actions per patent. After 12 months using the AI workflow, their allowance rate increased to 68% and office actions dropped to 1.8 average. That's a 51% improvement in allowance rate. With 80 patents per year, reducing office actions by 1.4 per patent at approximately $2,000 per response, they saved $224,000 annually. Let me conclude with critical best practices and common pitfalls to avoid when implementing this workflow. Best practice 1. Implement strict version control for all disclosure documents, prior art analyses, and claim drafts. Date and tag each iteration so you can trace the evolution of your invention story. Best practice 2. Always validate AI outputs, especially technical interpretations in prior art relevance assessments. AI is a powerful tool, but requires human oversight for critical decisions. Best practice 3. Explicitly document all assumptions in your analysis, including why you weighted certain features more heavily or why you excluded certain prior art from detailed review. Pitfall 1. Don't over-rely solely on semantic similarity scores. Legal patentability involves nuances that pure similarity metrics can't capture, such as motivation to combine or unexpected results. Pitfall 2. Avoid insufficient experimental documentation. Even with AI assistance, you still need rigorous contemporaneous records of experiments with proper controls and statistical analysis. Pitfall 3. Don't ignore prosecution history of cited prior art. The claims as granted may be significantly narrower than the disclosure, which affects their relevance to your invention. If you want to implement this workflow in your organization, here's a practical roadmap. Phase 1. Run a 3-month pilot program with 5 to 10 patent applications. Select a diverse set of technologies to test the workflow's applicability across your portfolio. Phase 2. Integrate AI tools into your existing patent management system. This might involve API connections, custom scripts, or commercial software depending on your infrastructure. Phase 3. Train inventors and patent coordinators on the new workflow. Focus on prompt engineering for disclosure refinement and interpreting similarity scores. Phase 4. Full deployment with continuous improvement. Collect metrics on allowance rates, office action counts, and time savings to demonstrate ROI and identify further optimizations. What metrics should you track to measure success? Here are the key performance indicators. KPI 1, first action allowance rate. Target a 20 to 30% improvement within 12 months. KPI 2, average office actions per patent. Target reduction from 3 to 4 down to 1.5 to 2.5. KPI 3, time from invention disclosure to filing. Target 40 to 50% reduction through streamlined documentation. KPI 4, cost per allowed patent. Target 15 to 25% reduction through fewer office actions and broader initial claim scope. Looking forward, how will AI continue to transform patent prosecution beyond disclosure and search? Trend 1. Predictive claim scope modeling. I will predict which claim scopes are most likely to survive prosecution based on examiner behavior patterns and citation networks. Trend 2. Automated obviousness analysis. Machine learning models will assess motivation to combine references and predict obviousness rejections before filing. Trend 3. Dynamic portfolio optimization. I will continuously analyze your entire patent portfolio to identify gaps, overlaps, and optimal continuation filing strategies. Let me summarize the key scientific principles underlying this AI-accelerated workflow. Principle 1. Systematically decompose the patenting process into discrete, analyzable steps where I can provide measurable value. Principle 2. Replace subjective judgments with quantitative assessments wherever possible, using metrics like similarity scores and risk indices. Principle 3. Embrace iterative refinement. Use AI feedback loops to progressively improve disclosure quality rather than seeking perfection in one pass. Principle 4. Base strategic decisions on data from your historical portfolio performance and continuous monitoring of prior art trends. Principle 5. Recognize that optimal results come from human-AI collaboration, not replacement. AI augments human expertise in disclosure, search, and analysis. Let's do one final back-of-the-envelope calculation to justify investment in this workflow. Assume an organization with an annual patent budget of $1.5 million covering 100 filings. Conservative estimate of 20% efficiency gain through reduced office actions and higher allowance rates. That's $300,000 in annual savings. Typical AI tool costs, including licenses, integration, and training, are approximately $50,000 annually. Net ROI is $250,000 divided by 50,000 equals 500%. This is a compelling financial justification for any organization with a significant patent portfolio. Thank you for your attention to this rigorous exploration of AI-accelerated patent success. The workflow we've discussed represents a systematic, scientifically grounded approach to improving invention disclosure quality and prior art search completeness. The key takeaway is that structure and quantitative measurement transform patent preparation from an art into a systematic engineering process where AI provides multiplicative value. I encourage you to begin with a small pilot program, measure results rigorously, and scale based on demonstrated ROI. The tools exist today. The question is whether you'll systematically deploy them.